V6 Codeless Application. This is a session that was given at Code 2012. There were two sessions to cover this topic of V6 Codeless Applications. The first was a lecture and a lab. This is covering the lab portion of the session. A V6 Codeless Application is an application that is developed in Knowledgeware. Even something like a graphic user interface can be defined using just Knowledgeware. Traditional programming languages are not required. During this session, we'll be creating an application that will build skateboard wheels. Then we'll be using those wheels to create a skateboard assembly. There's an application already developed to build the skateboard assembly, but our database is missing the wheels. Once the wheels have been generated, then we can generate the skateboards. We'll have a complete end-to-end application that will allow us to produce made-to-order skateboards for our customer. The end goal of this session is to create some skateboard assemblies utilizing the skateboard application. Before that can happen though, we need to create some skateboard wheels. To create the skateboard wheels, we're going to create an application to generate skateboard wheels. So your main focus in the beginning of this session will be to complete the skateboard wheel application. Once that's done, we can generate new skateboard wheel configurations. We have 30+ attendees in this session, so there'll be many options for skateboard wheels being populated in our database. Once those wheels start being populated, we can start creating new configurations of our skateboard in our made-to-order process. During this session, we have 50 minutes to complete our skateboard wheel application, generate some wheels, and then finally generate some skateboards. Due to that time constraint, much of the skateboard wheel application has already been defined. There are still many tasks that you'll need to complete before the skateboard wheel application can start generating skateboard wheels. This is just a preview of the steps that are already defined in the skateboard wheel application. The skateboard wheel application will access some templates, in this case power copies. We have two power copies that represent the whole pattern. One whole pattern is a circle. The other whole pattern type is a hex shape. And finally, we have a rim power copy. Utilizing these three power copies, we'll be able to produce many different wheel configurations. The example of the wheel application is pretty simple. In fact, you may be thinking, why not just create a design table? So I explored how many different wheel configurations could be generated. It turns out there are 60,000 different wheel combinations or configurations that could be generated given the parameters or constraints that we have in our specification. I think at that point it's not very practical to think about populating a database with so many different wheel configurations. Maybe the majority of those wheel configurations will never be used to generate a skateboard assembly. In the case of an application, the designer or engineer can get the specification to build a skateboard, generate a wheel specifically designed for that skateboard specification, and populate much less data in the database. Finally, after our wheel application is completed and we've generated many combinations of wheels, we're ready to start generating new skateboard assemblies. In the end, your skateboard assembly will look something like the picture here. So now let's get into CATIA and start looking at the details of the wheel application. First, we need to search for the application that exists in the database. So I'm using the search keyword kcomp, and then we have co-wheel already populated in the database for you. So we'll search for that. Double click on co-wheel to open it. And now we're in the automated design process workbench. Typically, to access this workbench, if we were starting something new, we'd go to the start button, Knowledgeware, applications, and select automated design process. We want to explore some of the features here in the interface. So I'm going to go back to the presentation. And what we're looking at first are the attributes that are associated to the co-wheel. These attributes have ranges or multiple values that we can use to input. We've already explored some of those ranges and values in the spreadsheet previously. Next, we could look at the operations. These are the steps or the sequence steps that are going to be executed during the application execution. Lastly, if we go to the resource table, we can look at the power copies that are going to be used during the execution of the application. Again, we have the rim. This is the definition of the wheel itself. We have two hole patterns, one being a hex shape pattern and the other one being a circular shape pattern. So now we can dive into the details of the application itself. Again, we see the class. We see the attributes associated to that class. And then we see the sequence and the behaviors of that sequence. This is a sequential process, meaning that this is the first step that will be executed, the second step, third step, and so forth. These steps are not completely defined for the purposes of our session. So our first task is to complete all the steps here and define them completely. To begin, we'll double click on Get Root. Get root means that we're going to get access to the product. When we first execute the application, it will open a product, and we want to get access to that product. The second step will be to change the description of that product. The third step will be to access the shape or the geometric document for that product. Once we get the shape, then we're going to access the axis system that's inside the shape. Then we're going to rename the axis system. We're going to instantiate the rim. We're going to instantiate the correct hole pattern, maybe the hex pattern or the circular pattern. And then finally, we're going to publish the wheel axis system. So to begin with, we have to define this get root. Here we'll type in external object. This will get us access to the product root. You can see the icon is now changed from a deactivation icon to an operation icon. So this icon indicates that this step is fully defined and ready to execute. In the case of a knowledge behavior, such as this one, we've done a little bit of scripting inside here so that once we have access to the root, we can access its description property and then set the value of the description. So what I'm going to do now is I'm going to create a link between these two steps. Here I have got access to the product root, and I need to pass the product root onto the knowledge language by creating this link. If I refresh the interface, I can see that I'm taking the output of get root and I'm passing it to the input of set root description. Now this knowledge language can access the product root and change its description. The next step is to define the get shape. In get shape, we need to say where we're starting from, and to get to the shape, first we need to access the product root. So we have access to the product root here. Again, I'll take the output and I'll pass it as the starting point for get shape. For the representation that I need, in this case, it is the shape. And now we can see that this one is fully defined. The next step, we need to get access to the axis system. So we'll double click on it. Our starting point in this case will be the shape. So first we got access to the root. Now we're getting access to the shape, and now we want to access the axis system. So let's expand that, and our starting point will be the output of get shape. In this case, we need to define a relative name. The relative name in this case will be absolute axis system. This is the name given to an axis system by default. So our next step, now that we have accessed the axis system, we need to change its name. So again, we've defined some Knowledgeware language here, and one requirement is to pass the object of the axis into the knowledge language. So again, to do that, we're going to create a link. So I'm going to take the output of the get absolute axis system and I'm passing it into the knowledge language rule. So now we can see that task is done. Let's take a look at the details of the rule itself. Again, we're defining the axis system, and the axis system has a property called name, and we're setting the name to wheel axis. So now instead of the axis being called absolute axis system, it will be called wheel axis. The next step is to define the instantiation of the rim power copy. So we'll double click on it, and we have several things to define here. First, the template type that we're going to define is a power copy. Next thing is the resource table here represents an ARM input, and we just have to type in the keyword rim. The destination will be the shape. So the shape is where all 3D geometry is stored or created. So our destination will be the output of the shape. The next step we want to do is we want to define the validation mode as best strategy. This will make sure that the values here that we're going to overload during the instantiation of the power copy will be taken directly from parameters, and we can avoid showing the power copy input panel by using best strategy. If we use something like inputs initialization, the power copy input panel would show up, and then we could do some manual selection inside the shape. But we want to automatically fulfill these parameters and avoid showing that dialog box. So that panel is defined. We can close it. We do have some more definition to define here. I've added some attributes, some custom attributes to this instantiation behavior. We need to overload the diameter, the depth, and the wheel axis. These are all inputs for this power copy. So to do that, I'm going to create a link between the diameter and our attribute diameter. Same for the depth. We'll create a link from depth to the depth attribute. And then for the wheel axis system, we will access the axis system from the rename axis system, the output. So let's collapse this and expand it. So we can see that we've created some link between diameter, between depth, and wheel axis system. And our instantiate rim power copy is completely defined. The next definition we need to work on is the instantiation of the hole pattern. So let's click on it. Same thing here. We have power copies that we're going to instantiate. We're getting them from our resource table. So we need to select ARM. But in this case, we have two different power copies that we could choose from, either the hex pattern or the circular pattern. So for this case, I'm going to show you a different way to make this a variable versus entering in the value that we want to access. In the case of the rim, there was only one option. In the case of the hole pattern, there are two options, so we have to handle it a little bit differently. The destination is still the same. We're going to instantiate the power copy into the shape, and same with the validation mode. We want to avoid showing the input panel for the power copy. Okay, so there are still a couple of things to deal with here as far as these attributes. So again, I mentioned that this is a variable, the ARM portion of the definition. We either want the hex or the circle. So we're going to make a link to the attribute that's been associated, because we know that this hole type has two definitions, either hex or circle. So just to remind ourselves of that, we can change that to be the hex or the circle. We can refresh it, and now we see circle. We can change it back to hex. We can do some refresh here, and we can see it's a hex. So we're going to take that value, and we're passing that value to the ARM attribute. And we need the number of holes. How many holes will be in our pattern? Let's make a link to that, to the hole pattern value here, so we know that this can be 3, 4, or 5. That value will be passed into the number of holes. If we refresh it, we can see the link has been made successfully. Then we need to select the axis system, so that again will be the output of the rename axis system. So we can refresh that, and we can see that the arm input has been defined by an attribute, the number of holes are defined by an attribute, and the wheel axis system is defined by the output of our rename axis system. Now the last step is we need to publish this axis system. The axis system will be used later to make a constraint when we put the axis system in the context of our skateboard assembly. In order to publish something, we need to access the root, the shape, and the object that we're going to create the publication to, which is in this case the axis system. We can take a look at the definition of that rule, and it's pretty simple. First we're just defining some temporary variables, then we're assigning some objects to the temporary variables. The objects are coming from these attributes, and then finally we're using this function to create the publication, and it needs the shape, it needs the object that we're going to publish, and it needs the name that we're going to give the publication. So we need to link these together with some of the things that we've already defined. So the root in will be linked to the output of get root. Then the shape in will be linked to get shape. And then finally the wheel axis system will be linked to the renamed axis system. Okay, so now everything in our design automated process has been completely defined. Of course we can do a save at this point. The last thing we need to do is generate a workbench. Workbenches are accessed through the start menu, and then here we can see that custom workbenches have been generated already. We're going to extend this menu with our new co-wheel workbench. To do that, we're going to use this icon, workbench definition. We're going to type in some identifiers here for our workbench. Then we have to define what type of workbench will be used in the initialization of the new document. So in this case it will be a product. And we'll save the results of this. Now if we go to the start menu, we'll see that we have a new workbench created here called build wheel co-wheel. We'd like to start a 3D part. Once a 3D part's been opened, we'll double click on the product. That will show us our workbench. The workbench is a product workbench. We're going to select this little blue character here, pick finish, and we can see we have a new representation. We have this object associated to our product called co-wheel. Underneath co-wheel, of course, we have our variables that we defined, and we can set these to whatever value we like. Remember, if we do something out of range, we immediately get a warning message provided by the Knowledgeware functionality. But we could enter in any value within the acceptable ranges. Once our values have been entered, we can go ahead and execute the application by selecting Make Wheel. Okay, great. So our wheel's been generated. We can review its geometric definition, and we could review the parameters, and sure enough our diameter is 35.5, the depth is 16.25. We have a number of holes being 4, and we can see that the circular hole pattern has been instantiated. So all the definition has been applied to this wheel, and of course we have our axis system, our wheel axis published. So now it's ready to be used in our skateboard application. So let's give this a name. Okay, propagate it. If we wanted to find another wheel, so we have a couple options to look at. It's the same process. Of course, we want some different values here. And we'll leave this as hex. Alright, now that we've defined the attributes, we're ready to generate a brand new wheel. Okay, so we have a new wheel that's been generated. In fact, let's dress this wheel up a little bit so it looks much different than the previous wheel we created. Alright, now we have two different distinct wheels ready for our database. Now we're ready to generate some skateboards.